students, this is Sindu KOUSHIK. In the previous class, I explained subspace and also problems related to subspace. So in this class, we will discuss the concept linear combination and linear span. Not only that, we will solve some problems related to linearly independent, linearly dependent. Okay. So let's start with the definition, linear combination.
Here is the definition. Linear combination of vectors. Let V be a vector space over the field F. That is V of F. Vector space over the field F. And alpha 1, alpha 2, alpha 3, so on alpha n be any n vectors. There are n vectors of V. C1, C2, so on Cn be any n scalars. So these are scalars of what? F, that is the field. Any vector of the form C1 alpha 1 plus C2 alpha 2 plus so on Cn alpha n is called linear combination of the vectors alpha 1, alpha 2, alpha 3, so on alpha n over the field F. So this is the definition. It means if I take scalars and vectors, here scalars, that is these come from field and here is the vector. Say this is come from the set V. So these scalars and vectors, if I pick one scalar and one vector, so joining by using multiplication, that is C1 into alpha 1 plus take C2 another scalar and alpha 2 another vector. So multiply those two, C2 alpha 2 for next C3 alpha 3. That is here the scalar C1 and the vector alpha 1 plus the scalar C2 and the vector alpha 2 plus the scalar C3 and the vector alpha 3 plus so on plus the scalar Cn, that is nth scalar, and the vector alpha n. So this is the linear combinations combining scalar and vector. Okay, so this is called linear combination of vectors alpha 1, alpha 2, alpha 3, so on alpha n. Is it clear? All the scalars come from the field and all the vectors come from the set V. Okay, so the set V is nothing but a vector space. So that is the definition of a linear combination of vectors. So once again, let V be a vector space over the field F. Alpha 1, alpha 2, alpha 3, alpha n be any n vectors and C1, C2, Cn be any n scalars. Any vector of the form C1 alpha 1 plus C2 alpha 2 plus so on Cn alpha n is called linear combination of the vectors alpha 1, alpha 2, alpha 3, so on alpha n over the field F. Is it okay? So next, linear span of a set. Next definition, linear span of a set. Here is the definition. Linear span of a set. Let V be a vector space over the field F and W be subset of V. Here I am taking one vector space and a field F and a non-empty subset W of what? V. Linear span of W is denoted by L of W. L of W stands for linear span of W. So it is defined by the set of all linear combination of finite elements of W. It means, see, L of W is nothing but it is the set of all linear combinations C1 alpha 1, C2 alpha 2 like this. Like that, the set of all linear combination of finite elements of W. Finite elements of W means alpha 1, alpha 2 are all elements of W. Is it okay? So that is linear span of W. Elements of W. So set of all linear combination. So L of W is nothing but set of all linear combination of elements of W. So elements of W are alpha 1 to alpha n. Okay, so that is L of W. L of W is nothing but linear span of a set. W is nothing but set of all linear combination of finite elements of W. Finite, here there are only n elements. So therefore it is finite set. So finite elements of W is nothing but L of W. Now L of W is equal to V means that is every element of V can be written as linear combination of finite elements of W. So here L of W is equal to V stands for, if I take an element of V, say X belongs to V, then it is equal to L of W. The elements of L of W look like the linear combination. Therefore, X is also look like C1 alpha 1, C2 alpha 2, so on, Cn alpha n. If I take another element, say Y belongs to V, then this element, which is also an element of V, but V is a linear span of W, therefore Y also look like the elements of L of W, C1 alpha 1, C2 alpha 2, like that. So I am choosing here D1 alpha 1, D2 alpha 2, so on, Dn alpha n. Here Di's is nothing but scalars, belongs to F, and alpha 1, alpha 2, alpha n are the elements of W. Is it clear? So that is nothing but linear span. So every element of V, that is for all Y belongs to V, can be written as, so Y is equal to linear combination of finite elements of W, that is C1 alpha 1 plus C2 alpha 2, so on, plus Cn alpha n is nothing but a linear combination of what? The elements of W. Elements alpha 1, alpha 2, alpha n are the elements, finite, in fact finite elements of W. Here alpha is belongs to F and Ci's, that is scalars, belongs to F. So this is the definition of linear combination. From this definition, we can define linear span of a set. Is it clear? So next, let us solve some problem related to linear combinations. So first problem in that, here is the first problem. Express the vector 3, 5, 2 has a linear combination of the vectors 1, 1, 0, 2, 3, 0 and 0, 0, 1 in V3 of R. So this is the question. So we have to express the vector 3, 5, 2 has a linear combination of vectors of what? In V3 of R. Okay, so linear combination means scalar vector C1 alpha 1 plus C2 alpha 2, like that. So here is the solution. We have to express the vector 3, 5, 2. So for that, take 3, 5, 2, which is equal to, that is the triplet 3, 5, 2, which is equal to C1. What is the alpha 1? Linear combination of the vectors what? 1, 1, 0, 2, 3, 0, 0, 0, 1. So C1 into 1, 1, 0 plus C2 into 2, 3, 0 plus C3 into 0, 0, 1. Is it okay? Here C1, C2, C3 are belongs to R, that is the field, scalars. So now 3, 5, 2 can be written as C1. If I multiply C1 within this, so C1 1s are C1, C1 1s are C1, C1 zeros are 0 plus 2 into C2, 2C2, 3 into C2, 3C2, C2 into 0, 0 plus C3 into 0, 0 plus C3 into 0, 0 plus C3 1s are C3. Okay. So now take first coordinate, that is C1 plus 2C2 plus 0. Is it okay? Second, that is C1 plus 3C2 plus 0. So I am just writing C1 plus 3C2. Now last coordinate 0, 0 and C3. So 0 plus 0 plus C3. Okay. So 3, 5, 2 is equal to C1 plus 2C2, comma C1 plus 3C2, comma C3. So now equate. Here we have the sign equal, therefore equate first coordinate, second and second, third and third. Okay, so here I am getting three equations, namely C1 plus 2C2 is equal to what? First one, that is 3. This is equation 1. Next, C1 plus 3C2, which is equal to what? 5. So that is second one. Next, C3 is equal to what? Third one, 2. So that is third equation. So from third equation, we clearly get the value C3, that is the scalar, third scalar value C3 is equal to what? 2. C3 is equal to 2. Now consider the equation 1 and 2. So if we solve this equation, we get C1 and C2 values. Okay. So now C1 plus 2C2 is equal to 3. C1 plus 3C2 is equal to 5. This is from 1 and 2. Now, here I am changing the sign. So, C1 plus C1 minus C1 gets cancelled. 2C2 minus 3C2 becomes what? Minus C2. So, 3 here is minus. Plus 5 becomes minus 5. Okay. So, here minus 5 plus 3 minus 2. Minus minus gets cancelled. We remain with C2 is equal to 2. Is it okay? So, now we get C2 value and C3 value. We need another scalar value. What is that? C1. So for that I am considering the equation 1. What is that equation? C1 plus 2C2 is equal to 3. C1 we don't know. Plus 2 into what is C2? Here is C2. 2. Which is equal to 3. C1 plus 2 2s are 4 is equal to 3. So C1 is equal to 3 minus 4. So 3 minus 4 is what? Minus 1. So C1 is equal to minus 1. We get all the three scalars values C1, C2, C3. Therefore, C1 is equal to minus 1, C2 is equal to 2, C3 is equal to what? 2. Okay. So now, write in that. So for this, you just write 3, 5, 2 is equal to, in place of C1, in place of C1 is what? C1 is minus 1. So that is, therefore 352 is equal to C1 minus 1 into 110 plus C2, that is 2. 2 into 230 plus C3, that is 2 into 001. Okay. So C1, C2, C3 for that. Okay. So we express this 352 vector has a linear combination of the vectors 110, 230, 001. Is it clear? So next question. Here is the next question, second question. Express the vector 1, 7, minus 4 has a linear combination of 1, minus 3, 2 and 2, minus 1, 1 in V3 of R. So we have to express the given vector has a linear combination. Linear combination means some scalar into vector, this vector plus C2, some scalar into this vector. Okay. So next, we want to find what are those scalars. What is C1 and what is C2? That is the final step. So let, I am choosing let 1, 7, minus 4 can be written as C1 into 1 minus 3, 2 plus C2 into 2 minus 1, 1. Okay. So here I am taking the given vector can be written as linear combination of vector. We don't know C1, we don't know C2. So we want to find what is C1 and C2. So for what value of C1 and C2 the equality holds. Okay. So now 1, 7 minus 4 as it is equal to, so multiply C1 within the triplet. So C1 into 1 C1 minus 3 into C1 minus 3 C1, 2 into C1 2 C1 plus 2 into C2, 2 C2, minus 1 into C2, minus C2, 1 into C2, that is C2. Is it okay? So now, first adding this C1 plus 2C2. Okay. Next, minus 3,1 plus minus C2. Minus 3,1 plus into minus C2. Okay. So last 2C1 plus C2. So 2C1 plus C2. So here we have triplet, here we have triplet. Compare those two. Compare those two triplets. So here first one, second one, third one. So we get 3 equations, that is C1 plus 2C2 is equal to 1, minus 3(1) minus C2 is equal to 7, 2C1 plus C2 is equal to minus 4. So equation 1, equation 2, equation 3. So now I am considering equation 2 and 3. Why I am considering equation 2 and 3? Here we have minus C2, here we have plus C2. So they gets cancelled. We remain with C1. And it means we get C1 values. If C2 are removed, then we get C1 value. That's for that I am considering equation 2 and equation 3. Consider equation 2 and equation 3. So here minus 3(1) minus C2 is equal to 7. That is the equation 2. 2C1 plus C2 is equal to minus 4. That is the equation 3. So now minus C2 plus C2 gets cancelled. Now minus 3(1) plus 2C1 means what? Minus 1C1, which is equal to 7 minus 4 is what? 3. So minus C1 is equal to 3. It means C1 is equal to minus 3. We get C1 value. So now consider the equation. Take any equations to find C2. You can take 2, you can take 3. So I am taking equation 1. Okay. So consider equation 1. C1 plus 2C2 is equal to 1. So in place of C1, we get minus 3. So substitute that one. Minus 3 plus 2C2 is equal to 1. So 2C2 is equal to minus 3 to the right become plus 3. So 2C2 is equal to 4. 2 ones are 2 twos are. So C2 is equal to 2. So we get two scalars C1 and C2. So for that C1 and C2 we have minus 3 and 2. 1, 7 minus 4 can be written as some scalar into that vector plus second scalar into second vector. So is it right? Equality, is it holds? So let's check this one. I am writing here minus 3 into 1 minus 3 2, 1 minus 3 2 and plus 2 into 2 minus 1 1. So let's check whether the right hand side becomes the left hand side, whether right hand and left hand side becomes equal. Let's check. So minus 3 ones are minus 3, minus into minus, plus 3 3s are 9, minus 3 2s are minus 6. Now multiply 2 within, 2 2s are 4, 2 1s are minus 2, 2 1s are 2. So now minus 3 first plus 4, comma, 9 minus 2, comma, minus 6 plus 2. Is it okay? 3 plus 4 plus 9 plus into minus minus 2 minus 6 plus 2. Okay. So this is minus 3 4 1. 9 minus 2 is what? 9 minus 2 7. Next minus 6 plus 2 is minus 4. We get 1 7 minus 4. Is it equal to left hand side? Yes, 1 7 minus 4. So it is clearly equal to 1 7 minus 4. So therefore our scalars are correct and it can be written as linear combination of these vectors. Is it okay? So this is the verification step. Next. So this is the second problem. Next problem, similar to the previous problems. So here is the next problem. Express the vector 2 minus 2 2. Express the vector minus 2 2 3 has a linear combination of vectors 1 minus 1 3 and minus 1 1 0 in V3 of R. So similar to the previous one, we have to express this vector as a linear combination of these two vectors. So for that, consider let minus 2, 2, 3 can be written as C1 into 1 minus 1, 3 plus C2 into minus 1, 1, 0, minus 1, 1, 0. So now multiply C1 within the bracket, C2 within the bracket. C1 one's a C1 minus C1 one's a C1, 3 into C1, 3C1 plus. C2 into minus 1 minus C2, C2 into 1, C2, C2 into 0, 0. Okay. So now first one, adding those C1 plus into minus minus C2. Next second one. So that is minus C1 plus C2. Last one. So 3C1 plus 0. So 3C1 plus 0. So we have the triplets in left hand side and also in the right hand side. So compare those two. Comparing first one, second one, third one. Comparing, we get 3 equations, namely C1 minus C2 is equal to what? Minus 2. Second one, minus C1 plus C2 is equal to what? Second one, 2. So minus C1 plus C2 is equal to 2. Next, third one, that is 3C1 plus 0 is nothing but 3C1, which is equal to what? 3. Okay, so from equation 3, we clearly get C1 value. What is that? 3C1 is equal to 3. 3 ones are 3. So C1 is equal to 1. We get C1 value. Now consider any equation, your wish, among 1 and 2. So I am considering equation 1. So considering equation C1 minus C2 is equal to minus 2. So C1, we know that value, that is 1, minus C2, which is equal to minus 2. So now take minus to the left, minus 2 becomes plus 2, which is equal to minus C2 becomes plus C2. So 1 plus 2 is nothing but 3, which is equal to C2. C2 is equal to 3. So we get C1 and C2. Ma'am, if I consider equation 2, we get the same value as C2. Your question is like that. Answer is yes. So here is the answer. Minus C1 plus C2 is equal to 2. This is the equation 2. Minus C1 is what? 1 plus C2, which is equal to 2. So minus 1. 2 to the left, minus 2. 2 becomes minus 2. And plus C2 becomes minus C2. Minus 1, minus 2, minus 3, which is equal to minus C2. Minus gets cancelled. C2 is equal to 3. Okay, so C2 is equal to 3. Both are same. You can put for any equation, you get the same value. Okay, so now for this one, C1 and C2, we get C1 is 1 and C2 is 3. So therefore, last conclusion, minus 2, 2, 3 can be written as a linear combination of vectors and with the scalars 1 into 1 minus 1, 3 plus C2, that is 3 into minus 1, 1, 0. Is it clear? So next question.